inclines. Our objective is to be able to create a mathematical model to represent the motion of an object moving up or down a ramp. So to start, we need to create some definitions and decide what we're actually talking about when we are talking about an inclined plane. So we have our inclined plane. This here is the incline. There's usually some object on it. It may be moving, it may not. But we have the force due to gravity. The force due to gravity is the same as always. It's pointed down toward Earth. Then we have the normal force. And if you remember, the normal force is perpendicular to the surface. Our surface is right here. So we want this to be perpendicular. Okay? And then the force due to friction is opposite of motion. And we can have an applied force going up or down the ramp, usually you won't always have these two. Sometimes it's a frictionless surface, sometimes the only force acting on it is gravity. So you just have to read the problem and see what's going on. All right. Now, if you look at this, you can see that there is an angle involved here. So there's an angle. If there's an angle, and we do have the force applied and the force due to friction, if we keep it like this, we have to break down Fn, Fa, force due to friction, into x and y components. Because these are our axes. I don't know about you, but I don't want to do that. That is a lot of x and y's I have to keep track of. So what I'm going to do instead is I'm going to change things. So I'm going to draw our ramp again, but this time I'm going to change the way our axes look. So I'm going to make the axis go with the incline, and I'm going to call this parallel because wherever we move this up and down, it's parallel to the surface of the ramp. And then I'm going to make this axis perpendicular. That's just its name. It's perpendicular because this right here is perpendicular to the ramp's surface. Okay? So if we do that, we still have the force due to gravity. We have the normal force. We have the force due to friction. And we have the applied force. But now the only component we have to break down into, the only force we have to break down into components is the force due to gravity. I like this way much better, much simpler. Okay, so now the next part is to figure out how we break it down. We know we use sines and cosines to break something down into components, but we have this ramp, we have this angle, this is force due to gravity, this is one angle, this is one axis, and this is another axis. It's supposed to be parallel. I didn't draw it super well. What else is new? So now we have to figure out what angle are we going to use. How are we going to make it? We have this angle, but that's the only one that we are given. So for the next part, this is too long, didn't read. The short answer is this is theta 1, this is theta 3, this is theta 2. Theta 1 is equal to theta 2. Those not interested? Skip to sine theta is equal to opposite over adjacent. You can skip, opposite over hypotenuse. You can skip ahead to where I start talking about this, okay? But for those of you who want to know how on earth I get that theta 1 is equal to theta 2, let's just look at this pretty briefly. So we know that a triangle is equal to 180 degrees. So in this case, we have theta 1, theta 3. This is a 90-degree triangle because it's going straight down. So this is going to be theta 1 plus theta 3 is equal to 180 degrees. This is plus 90 because I accidentally skipped it. So then we can get rid of the numbers, minus 90, minus 90. So theta 1 plus theta 3 is equal to 90 degrees. Okay? We can solve for theta 1. It's equal to 90 minus theta 3. Also, we know that this is perpendicular right here, so it's 90 degrees, which makes this right here also 90 degrees. So theta 3 plus theta 2 is equal to 90 degrees. And if we solve for theta 3, if we solve for theta 2, we can see that theta 2 is equal to 90 minus theta 3. So this is 90 minus theta 3. This is 90 minus theta 3. So that means that theta 1 is equal to theta 2. Okay? So this right here is given to us by whatever they give us in the problem for the inclined angle. Okay? All right. So now we are looking at our ramp again. This is theta. This is the box. Force due to gravity. We want parallel. And we want perpendicular. This is going to be the force due to gravity parallel. It's just taking this component and making it a part of this axis. And then this is the force due to gravity perpendicular. We're just following this axis. So now we're just trying to find the components. So we can say that sine of theta is equal to opposite over hypotenuse, and that is going to be the force due to gravity parallel over the force due to gravity. And then we can solve for the force due to gravity parallel, so we get force due to gravity times sine theta is equal to the force due to gravity parallel. Okay? So if you look at this, this one refers to this here. It's going down the ramp. So we can say that sine slides down the ramp to help you remember. Okay, so it's the sine 1 is the force due to gravity parallel, which is the one that goes down the ramp. So you sine slides. So in case it wasn't obvious, this is not in the reference table. Okay, so then we need the force due to gravity perpendicular. We can do the same kind of thing, but this time it's going to be cosine theta is equal to adjacent over hypotenuse, which is equal to the force due to gravity perpendicular over the force due to gravity. So then we get the force due to gravity perpendicular is equal to f of g cosine of theta. So then we have broken this into components, okay? And the next time I see you, we will work on putting this into practice.